Using a couple of simple decays, we're going to work out what the quark structure of the lambda 0 particle is. And if you're doing A-level physics, you're going to want to hang around to the end, because I'm going to introduce to you what is probably going to be a new and really weird thing about the pi-0 mesons.
The first step to getting the lambda 0 particle in the second equation is to in fact get the xi0 particle from the first equation. The omega minus particle, which consists of three strange quarks, decays into a xi0 and a pi minus. So our first task really is to identify what a pi minus is. Now we know that all mesons are made of a quark-antiquark pair. And we also know that the strangeness is going to be 0 because it's pi meson. Try d anti-u. See what happens this time. Well, the d is minus 1 over 3 and then anti-u is minus 2 over 3. Haha! That does in fact add up to minus 1. And that is in fact the combination, but we now have to think about what's going on in our xi0 particle. So what we know is that if this was a strong interaction, then strangeness would have to be conserved. Given the pi minus has no strangeness, this would mean the xi0 particle and the omega minus particle would have to have the same strangeness, minus 3. In other words, there would be no reaction here because these two are identical. So that tells us then that this has to be a weak interaction. And in a weak interaction, what will happen is that one quark will decay into something else. In other words, we know that we're going to have two strange quarks here. And then the question is what is the other particle? Let's try the u particle, or the u-quark I should say. So that again, the two strangenesses will give us minus 2 over 3, and the up quark will be plus 2 over 3. So that is in fact what we're looking for. It's going to be an up quark. It can't be an anti-up quark because then that charge would become minus, and so we'd have a really odd charge there. In fact, a non-possible charge. So the xi0 is SSU. So next up then is to get the structure of the lambda 0. So looking at the second reaction, then we start off with the difficult to draw xi0, which we just worked out is SSU. And then we make the lambda 0 and pi 0. Now it's pretty much the same sort of procedure here. So the only way to get a pi 0, in other words a neutral pion made of a quark-antiquark pair with no strangeness, is in fact to have an up anti-up or a d anti-d. And in fact it could actually be either of those in this case. Now we've got to think about the lambda 0, which we know has to have a 0 charge and 3 quarks. So could it be possible that the two s's remain unchanged and then we have any combination of like u, anti-u, d or anti-d? Now if you go through all those options, it clearly can't be SSU because then it hasn't changed. If you go through all of those options, none of them will give you a 0 charge, so it can't be any of those options. So that therefore means that actually what has to happen is that one of our s's has to change and then the u stays fixed. So the question is, what does this other s change into? At d in, we will now get a charge of minus a third, minus a third, plus 2/3, and so that could work. And if you go through the various other combinations for what that middle particle could be, you find that that is in fact the only option. So our lambda particle is going to be a SUD. This is all fine and dandy, at least for the lambda particle, but it does give us a rather interesting question of which of these two combinations of quarks do we have for the pi 0? Well, as with all things particle physics, it's not that simple. What we end up with is a crazy mixture of both at the same time, a superposition, which is a word that might remind you of wave behaviour when two waves meet. If you found that video interesting, why not try this one?